Hello and welcome to this week's Hardware Systems Collective seminar. Today we are grateful to have Christopher Batten as our guest. He's an associate professor in the School of Electrical and Computer Engineering at Cornell. His interests a wide variety of things, including architecture, EDA, and VLSI. He's had a very distinguished career and has won quite a few awards. Even just looking only at early career young investigator type of awards, he has those from Air Force, Intel, NSF, DARPA as well. So just to give you a sense. And with that, I'll be happy to introduce Chris and let him take it away.
Okay, thanks, Scott. So I'm excited here to talk to you a little bit about what I think is a new era of open source system on chip design. And so I'm going to start by discussing some trends that motivate why I think it's a particularly exciting time to be contributing to open source hardware. So this plot shows 4 key metrics for high performance processors over the past 4 decades. Shows the number of transistors per die, shows single thread performance as captured by second, shows the processor clock frequency and typical power. And so, of course, as many of us know, there was a golden age of computer architecture up until about 2005. Moore's law was providing a wealth of transistors, and then architects could leverage these transistors to do all kinds of cool things like deep pipelining and out-of-order processing and such. Because, of course, unfortunately, you can kind of see typical power creeping up. And around 2005, as most of us know, there was a sea change and industry turned to multi-core processors to try to make up for kind of the power limitations and corresponding implication on processor clock frequency. But a multi-core processor is not a silver bullet. And so increasingly parallelization along with specialization are key architectural techniques being leveraged in hardware design. And when I say hardware specialization, I mean it broadly to cover everything from vectors and GPUs to FPGAs to more truly application-specific accelerators. So hardware specialization is being leveraged across the computer spectrum from the cloud to IoT. So this is represented by things like the Google TPU for machine learning in the cloud, but also a very cool chip, the Nvidia's Mirror 2. So this is a chip specifically designed for more edge machine learning in computer vision. And this is creating a kind of a wealth of chip startups. I don't think, 5 or 6 years ago, you would have seen this many chip startups kind of coming out, being funded by venture capital. A lot of them are in the machine learning and some of them in the graph processing space. But this begs the question, what else can we do to accelerate innovation in accelerator-centric system on chip design? And to kind of answer this question, we might want to be inspired by looking at kind of how software innovation happens today. So let's say you have some cool idea for a new iPhone app or something, and you want to basically explore doing a new platform based on this idea. So your value add is your proprietary code. And so, for example, Instagram wants to come up with a new kind of photo sharing app. They can start with $500K of seed funding, 13 people, and then grow to an over $1 billion company. And how do they do this? Well, they do this because it looks like they're climbing a mountain to reach this kind of peak of producing some kind of interesting product, but invariably it's more like climbing an iceberg. Much of it is hidden beneath the surface. So as you probably know, like 90% of the volume of an iceberg is hidden beneath the water surface. And in this analogy, what that represents is the open source software ecosystem. And Instagram has actually been really upfront about how much they were able to leverage the open source software ecosystem to bootstrap the process when they were just starting out. And this included everything from different programming languages like Python and frameworks like Django, but also backends and databases like Memcached and SQL and all kinds of other frameworks to help them quickly get to a minimal viable product. So what about hardware innovation? Hardware innovation is nothing like this. There is nothing hidden. It is truly like climbing Mount Everest. It is not a small hill. It is indeed a true mountain. So if you want to build a new machine learning accelerator, like that's your value add, there's all these other components that you have to build or you might have to buy to basically do what you need. And all of it, or much of it, is closed source. So things like ARM processors, ARM on-chip interconnect, but also things like physical IP, like standard cells and I/O pads, or maybe memory controller PHYs, SRAM memory compilers. And then there's all the EDA tool flows that go around this that are often and primarily closed source, things like simulators for RTL simulation and gate level simulation, but also your synthesis and your place and route tool and your formal equivalence checkers and your prime-time static timing analysis tool and your signal integrity checker and your supply voltage analysis tool, and then all your like physical verification tools like your DRC, your extraction, your LVS tools, and then your transistor level spice simulation. All of this closed source and proprietary infrastructure is required to innovate in hardware right now. And this is one reason why chip costs are skyrocketing, right? So it can cost over $100 million to do like kind of a state of the art, significant chip tape out nowadays. So, and that, keep in mind, Instagram, right? Instagram started with 500K, right? So, if you're trying to do a chip startup, and your pitch is that, oh, you give me $120 million and I can get you to a minimal viable product. I mean, which one are you going to fund? 500K or over $100 million? So what can we do about this? Well, how can we bootstrap the process and allow chip startups and to get to a minimal viable product or prototype more quickly? So for one thing, often when you're trying to shoot for a minimal viable product, you don't necessarily need to be in the most cutting edge technology, right? So you can use an older technology, especially with the slowing of Dennard scaling. The hit is maybe not as much as you might think. This might be a great way to prototype your new research idea. And indeed, in some IoT or mixed signal platforms, older technologies are actually preferred. So that gets you kind of reduces some of the mass costs, but you're still left with the significant software and hardware development, testing, and verification costs. So can we use open source software and hardware to help address some of these remaining costs? So let's think of now some of the equivalence between the software and the hardware open source ecosystems. So on the software side, we have high-level languages that are open source, like Python, Ruby, R, JavaScript, Julia. We have a lot of libraries, like the C++ standard template library, but also, for example, the Python standard libraries. We have whole systems, open source systems, like a Linux, Apache, Memcached, and we have a lot of standards like POSIX, and then tools and tooling that goes along with like compilers and runtimes and JIT technology. And then what goes along with this is not just the open source actual infrastructure, it's also an open source mentality, right? So kind of the trend towards agile software design, the ability to leverage, infrastructure as a service and elastic computing to help bootstrap and facilitate rapidly doing software innovation. What happens if we take a survey of what's going on in the open source hardware side? There's actually a lot of excitement and going on the hardware side as well. There's been a resurgence of cool new high-level languages. Some of you have been learning about some of these in Scott Beamer's class, right? So Chisel is a great example. PyMetal I'm going to talk to you about today, but there's also other frameworks like PyRTL, which you might be familiar with, MyHDL. Basically you name it, and people are thinking about creative new ways to build high-level languages for open source hardware design. There's also kind of starting to become an ecosystem for libraries, and examples BaseJump out of UW by Michael Taylor. And then systems as well, open source, increasingly capable systems like Rocket, Arion, OpenPython, Boom for out of order execution, and then standards. Most of you probably know about RISC-V, and the beauty of that is an open source standard, which kind of serves the same purpose of POSIX, but in the hardware ecosystem. And increasingly other types of open source standards like, ROC for co-processor interfaces or TiloLink for cache coherent memory systems. And then the tooling has come along too, right? So we have kind of the age-old Icarus Verilog, but Verilator is under active development. Qflow, Yosis, ngSpice, all these under active development. And there's a lot of excitement about agile hardware design, which kind of to complement agile software design. And we can leverage information infrastructure as a service traditionally we think about it as elastic computing. You can also think about this for elastic CAD, allowing you to scale out quickly with open source tools to explore a design space as you think about hardware innovation. So 2 years ago, I got to go on my sabbatical. One of the fun things about sabbatical is you get to sit around all day and brainstorm and kind of tinker and do coding. And so one of the things I wanted to do is see like what's the minimum number of commands in order to basically push a design through the flow using kind of the state of the art in open source CAD about two and a half years ago. And this is what I came up with. My goal is to get to fit on a single slide. And I checked a couple months ago that all this still works if you use an Ubuntu server on Amazon EC2. You can basically leverage Yosis, Graywolf, and QRouter. You can leverage kind of open source, super old technology, standard cells. You can leverage Magic, which is still under active development, and K-layout. And if you do these commands, at the very end, you will indeed get layout. Now, if anybody's done chip design, you'll look at this and be like, that's not really layout. That's a toy. I can count the number of cells, right? I can probably count the number of transistors. Where's all the other parts that make up a chip? And of course, that's true. But what I beg you to remember is what the history of open source software looked like. And when Linus Torvalds first introduced Linux, right? He said, I'm doing a free operating system, just a hobby, right? Won't be big and professional like GNU for x86 clones. So when open source software really started to get going, it was also thought just as kind of a hobby and a toy. And I think this is where we are now, right? And in terms of open source hardware. And therefore, I think in 20, 25 years, open source hardware could very well be the way you build chips, cutting edge, state-of-the-art chips, just like open source software is the way you build, cutting edge, state-of-the-art, for example, clusters. Now, a lot's changed even in 2.5 years, to be honest. So, for example, Open Road, which is being led by UCSD and Andrew Kong there under the DARPA IDEA program, is a really awesome example of essentially open source EDA and pulling together a lot of open source tools to kind of bootstrap and amplify the process, and then building on top of that. And you also see somebody you might recognize here. So here's Matt talking about basically being able to leverage some of this Open Road infrastructure for his own work. Open Road actually does work. So this is an example of kind of using Open Road to push through the flow a simple RISC-V processor in a 65 nanometer technology, and they're making great progress in more advanced technologies as well. So all of this, I think, gives us hope that open source hardware has a real future, and I think it's a particularly exciting time to basically be involved in this kind of activity. So what I want to do today is talk to you a little bit about two pieces of work that we are doing in my group, and then previously worked on in my group, or contributed to my group, which kind of illustrate different aspects of this open source hardware ecosystem. And then I'm going to end with a call to action to try to encourage all of you to get involved. So start by talking about a first piece of work. This is the PyMetal 3 framework. So let's motivate why we developed and are really excited about PyMetal 3. So there's two ways to think about the motivation for this project. So the first is to think about multi-level modeling methodologies. If you have a new research idea in computer architecture, particularly nowadays where often it is cross-stack and spans everything from applications to transistors, you're going to need a variety of different tools to help explore that research idea. So you're going to want to do some functional level modeling at a very high level where you're just capturing the behavior of the hardware accelerator, for example, you're interested in exploring. You're going to want to do some cycle level modeling. Here, you're going to bring in cycle approximate timing models, maybe some analytical area energy and timing analysis. And then you're going to probably want to do some RTL modeling, because invariably, the analytical area and energy timing models you have access to don't model the cool accelerator you're trying to build. So you'll complement that maybe with some RTL modeling. Here you can use kind of cycle accurate timing and gate level area energy and timing analysis. So this kind of cross-stack research really requires a kind of a variety of different modeling methodologies. And unfortunately, that brings along with it a lot of baggage. Each of these different levels of modeling has its own frameworks, its own languages, its own tools, but perhaps most importantly, its own design patterns, its own way of thinking about how to do the modeling. At the functional level modeling, it's a pure software engineering exercise, often using maybe a productivity level language. Maybe you're doing some algorithm development in Python or something, or maybe you're building a C++ ISA simulator. Cycle level modeling is also very much a software engineering exercise, right? It doesn't feel like writing hardware. What it feels like is building a really complicated, sophisticated C++ software engineering project. And examples of this, for example, might be like Gem5, complemented with something like BigPad. And the RTL, you're completely different. RTL, now that's truly a hardware engineering exercise. You're using something like maybe Verilog or VHDL and using an EDA tool flow. So this is what we term the multi-level modeling challenge. So essentially the fact that functional level, cycle level, and RTL modeling use very different languages, patterns, tools, and methodologies. System C, if you're familiar with it, is a good example of a unified multi-level modeling framework. It's in C++ and provides a variety of features that allows you to model everything using kind of algorithmic all the way down to RTL. But if anybody's used System C, I think you would share with me the question, is that really the best we can do? Is System C really the best we can do with respect to productive multi-level modeling? Can we do better? And so this is one of the motivations for this work. The second motivation comes more from the kind of the pure RTL VLSI side of things. So if you think about traditionally like RTL design, just focus on that aspect of chip design. If we're just going to use a hardware description language like Verilog, this is what the develop methodology might look like. Our designer writes some RTL, then does some simulation, writes some test benches. All of that will be in a single language, a single framework, for example, using Verilog and Verilog simulation. So this has a fast edit sim debug loop. You have a single language for kind of structural, behavioral, and test benches, but it can be very difficult to create highly parameterized kind of generators. And I would argue these generators are critical to the notion of the open source hardware ecosystem. We want to create highly reusable components which can be open sourced and used in a variety of different contexts. So, for many, many decades, you take your favorite scripting language and people have either embedded Verilog in it or have embedded it in Verilog, right? So, I don't care if it's like, Ruby, or I'm sure somebody's come up with some kind of MATLAB Verilog composition. People are always gluing these things together, creating hardware pre-processing frameworks. So now for example, in like Genesis 2, I'll use a mix of Verilog and Perl, and then I'll basically kind of run the Perl script and it'll generate a bunch of RTL. My simulation is still on the Verilog side. Maybe I'll generate test benches as well. So this has a slower edit sim debug loop, but more importantly, there's like this semantic gap. Like the Perl knows nothing about hardware semantics or nothing about Verilog. It's basically doing kind of string text processing. And that can be very error prone and very frustrating. Although it does make it easier to generate highly parameterized generators. So these disadvantages raised interest in what I would term hardware generation frameworks. And Chisel would be a great example. So in Chisel, basically the host language is Scala. And here you're not just going to generate the structure, you're also going to put the behavioral code itself as a first-class citizen in the host language. So, but with these hardware generation frameworks, you're still generating RTL and then doing all of your RTL simulation over here in Verilog. And the test benches, you're still having to generate your test benches too, because kind of with traditional Chisel, like all of your simulation is happening over here. So you have a single language for structural behavioral, but not as much for the test benches. It can be a little hard to write really powerful, flexible test benches in this way. That you kind of have a slower edit sim debug loop. But the key challenge is that you cannot leverage the beauty and the power of the host language for verification and testing, which many would argue is actually the critical, the long pole in terms of trying to make chip design easier. So this again raises the question: is Chisel the best we can do in productive RTL design methodologies? So PyMetal 3 is kind of our solution to addressing these challenges. PyMetal 3 is a Python-based hardware generation simulation verification framework, which we would argue enables productive multi-level modeling and RTL design. So with PyMetal 3, you can build functional level models in Python. You can build cycle level models in Python. And you can also do RTL design in Python. And you can write your test benches using all the power and all the features of Python that anybody who's used Python knows and loves. Critically, the simulation is also in Python. So you don't need to translate it into some other HDL before you can start doing your debugging and simulation. We provide a fully pure Python simulation kernel, which allows you to mix and match these different levels of abstraction and do all your verification and testing in Python. Once you're ready and you have an RTL model that you're happy with, then you can generate system Verilog. And we have features to allow you to pull that back in and do co-simulation. So you can reuse all the same test benches you had before to verify that your translated Verilog is correct. And once you're happy with that, you can synthesize the design either for an ASIC or an FPGA. And we also have features that allow you to take the synthesized ASIC or FPGA and again, bring it back into the simulation framework to allow you to run the exact same tests on your actual prototype. This is the vision for PyMetal 3. So PyMetal 2 was the first version of PyMetal. It was released in 2014. We gained extensive experience in it and used it quite a bit in our research and teaching. PyMetal 3 is the brand new version of PyMetal. It was officially released in May 2020. For one thing, it adopts Python 3. PyMetal 2 uses Python 2. And had a significant rewrite from the ground up to improve productivity and performance. Has a much cleaner syntax, we think, for some of the CL and FL and RTL modeling. Has a completely new, much more robust Verilog translation support, and also has first-class support for method-based interfaces, which are critical, for example, for transactional level modeling or high-level modeling. So let me just give you a whirlwind tour of what PyMetal 3 looks like. So you write your model in Pymetal 3, essentially using a class library, an embedded DSL. You write your configuration in Python as well. And then you elaborate your design. And what you end up with is a model instance. This is an in-memory intermediate representation. Unlike something like Fertile or LLVM, this is kind of a standard in-memory Python representation. And the beauty of Python is using introspection and reflection features, you can manipulate that in-memory representation. And you do that using things called passes, so Pymetal 3 passes. These passes are working at a higher level of abstraction than, for example, what you might do if you write a Fertile pass. So Pymetal 3 passes do everything. So for example, the simulator is a Pymetal 3 pass. Essentially, you use a Pymetal 3 pass to generate a simulatable model. You don't like our simulator? No problem. Write your own Pymetal 3 pass to do your own simulator. In fact, we've tried lots of different simulators which have different trade-offs with respect to fidelity or capabilities. It really enables you to explore and play around with simulation because it's not baked into the underlying kernel. Translation, so translating to Verilog, that's another pass. You want to translate to Fertile, we've looked at that. You can write a translation pass for Fertile. You want to translate to System C, we've looked into that. You could write a translation pass. And then there's a whole bunch of other passes you could do to do analysis or to do transformations. So this is a high-level idea of the Pymetal 3 framework. So let's just see what some Pymetal 3 code looks like, just to give it a flavor for it. So here's some high-level modeling using Pymetal 3. So you can create functional level models. So for example, here's a Q. This is a functional level Pymetal 3 model. It inherits from the component base class. It uses a construct method to construct the hardware. And then it provides some methods to manipulate that data structure and some decorators to indicate that these are Pymetal 3 methods, and has support, for example, for blocking and non-blocking method interfaces. So this looks very much like kind of normal Python code. There's some decorators and such. But this kind of has special semantics which allow you to, for example, structurally compose them. So for example, over here, I'm making a double queue. So I've got a Q1 and Q2, and I have some logic where I want to move some data from Q1 into Q2. You can do that by instantiating the two queues. You can connect them structurally because these method-based interfaces are first-class citizens in the framework. And then you can create what are called update blocks. So update blocks are essentially concurrent processes which allow you to do logic. And so here, essentially, if the D queue is ready and the N queue is ready, I can move some data from one queue into the next queue. So this is kind of much higher functional or maybe even transactional level modeling, which is enabled in the Pymetal 3 framework. Now you can also do much lower level modeling. You can do kind of like standard Verilog looking RTL modeling in Pymetal 3. In fact, if you like Verilog, you could very easily get started with Pymetal 3. No need to use some crazy new syntax and some crazy new abstractions. There's kind of a very nice mapping. So if you're creating a registered incrementer here, for example, my module has an input port, an output port, has a register, has a +1 increment logic. In the construct method, I declare my ports, input port, output port. I've got a wire. I've got an update FF block. This is very much analogous to an always at pause edge clock block. I've got an update block, very much analogous to an always at star block in Verilog. Here we've got some sequential logic. We've got a non-blocking, something that looks like a non-blocking assignment. Here I've got some combinational logic, something that looks like a blocking assignment. And so if you feel at home in Python and Verilog, you can get started in Pymetal 3 code very, very easily. So some people might ask me at this point, it's like, oh, well, if it looks so much like Verilog, what's the point? What's the benefit? And I would say, like, you're missing the point. The hard part is often not the design. The hard part is creating the generator and the verification and the composition and the testing, all of that. So that's where you get to use all the power of Python. And then you can layer high-level abstractions on top of this as well. But we think this is a feature, not a bug, because it allows you to kind of very quickly get started with Pymetal 3 if you're familiar with for example, Verilog or VHDL. Okay, so first-class support for composing Pymetal 3 components and Verilog was a key design goal right from the beginning of building both Pymetal 2 and Pymetal 3. And in Pymetal 3, it's only gotten better. So what do I mean by that? So you could take a pure Pymetal RTL instance, and you can run our translation pass, and you can generate system Verilog, readable system Verilog. Then we also have an import pass. So an import pass essentially around your system Verilog component, and it will create a C wrapper and a Pymetal wrapper. Then we can use Verilator to take the system Verilog and create some C++ source code that corresponds to that Verilog. We can use LVM or GCC to compose the C++ generated from Verilator with our C wrapper to create a C shared library. And then we can use kind of the powerful features of Python as a glue language to easily import this C shared library into a new PyMetal wrapped component. And this is all automated, purely very, very seamless to do. So this allows you to, for example, easily test that the translated Verilog matches what you thought it should. You can rerun all your tests on the translated Verilog. It also allows you to easily import external Verilog. So instead of running the translation pass, you just take some system Verilog. So for example, UC Berkeley hard float or an Arion core. Take some system Verilog. As long as Verilator supports it, we can wrap it and you can test it and you can bring it into the PyMetal 3 framework as a black box. As a cool effect, it also kind of acts like a JIT. So if your PyMetal 3 RTL model is too slow and you're pretty sure that it's correct and you're not going to change it too much, you can essentially run this translation pass, and what you'll end up with is a highly performant compiled C++ model of your RTL design that then you can simulate using PyMetal 3 around the outside. So this has a lot of cool benefits. So at this point, I think it's really important to emphasize what PyMetal 3 is for and what PyMetal 3 is not for. So PyMetal 3 is for taking an accelerator design from concept to implementation, or creating highly parameterized cycle level RTL models or RTL design generators. It's specifically well suited to rapid and agile design, testing, and exploration of hardware mechanisms. And it's good at interfacing with other C++ and Verilog frameworks, owing to the kind of the nice features of Python in the first place. So PyMetal 3 is not currently for high-level synthesis. You cannot write arbitrary Python code and have it turn into hardware. Don't worry, we're exploring it, but that's really hard. Okay, so it is not for high-level synthesis. If you want to transform a functional level model into, example, a CL and RTL model, currently that is a manual refinement process. It's not for many core simulations with hundreds of cores. We spent a tremendous amount of time making the framework fast, but it's not that fast. So in that case, you might want to use a different framework, or you might want to use PyMetal 3 to generate, for example, Verilog, and then you could compile that and use it separately. It's not for full system support with running a real operating system and booting Linux. All right, that's just not where it's at right now. And it's not if you need right now an out of order processor that supports speculation, memory disambiguation out of the box, and you just want to download and use it. We don't have that yet. We're working on it, but we don't have that yet. So I think it's important to clarify what PyMetal 3 is for and what PyMetal 3 is not. All right, so let's do a demo. So one of the beauties of kind of like this format is we can do a live demo. Live demos are always fun because they have a chance for a spectacular failure. So we'll see how well this works. All right, so I'm here on my laptop. First thing I'm going to do is I'm going to make a directory to do my demo in. And one of the things we actually spent a lot of time on in PyMetal 3 compared to PyMetal 2 is thinking critically about how to make it easier to package and use. So one thing we did is we bought into the Python packaging system. And this has a lot of really cool benefits. So here I'm creating a virtual environment. And I'm going to go ahead and activate that virtual environment. And then I'm just going to use pip install PyMetal 3. So this makes it very easy to install and use the framework. All right, you don't need to clone a repo, and you get this completely isolated framework. And here we get to piggyback on the powerful kind of packaging and isolation frameworks associated with Python. It also makes it really easy to distribute IP. You can just pip install PyMetal 3 - your favorite IP, right? All right, so now I'm going to pip install IPython to make it a little easier to use. Being able to leverage the Python ecosystem has all kinds of nice benefits with respect to testing or development environments or debugging, and like I said, also packaging. All right, so now I'm going to go ahead and start up the interpreter. All right. So first thing I'm going to do from PyMetal 3, import star. So that gets me kind of the core DSL. So any good hardware language has to have support for like fixed bit with types. So here I'm going to create an 8-bit type. I'm going to initialize it with the value 6. Has the value 6. We can see that now. I'm going to create another 8-bit type. I'm going to initialize that with the value 3. It's got the value 3. Good. And of course, we have all the standard kind of like bitwise operators. You'd be surprised how much we debated the exact semantics of these operators. There's a lot of different ways you can define semantics in corner cases with kind of bitwise operators. So you can do shifts and you can do concatenation. You can do ORs or whatever. So here's another one. And you can also do slicing and So here's like slicing out a few bits. Okay, so that's our bits type. So that's kind of a key data type we'll be using. All right, now as part of PyMetal 3, we include some kind of examples right in the framework itself. So here I'm going to basically import an example. It's a very, very simple example. It's a full adder. So here I'm importing the full adder. And because we want to see what the code looks like, I can use Python's inspection features to go ahead and print out the code. So here I'm going to inspect the source code corresponding to the adder that's in the framework. All right, so let's take a quick look at this. So we have a full adder, inherits from the PyMetal 3 component base class. And the construct method, we construct the hardware. It's got 3 input ports and 1 output port, 3 1-bit input ports, 2 1-bit output ports, has a single update block, which is a combinational block. And it does what you think it does. So the sum computes the sum output, and the cout computes the cout output. All right, so I've got a piece of hardware here. Now, if I was using something like Chisel, the next thing I would have to do is generate some Verilog, and then I have to switch gears and go write some Verilog to test it, or maybe peek and poke some Chisel code to test or something like that. Instead, let's just go ahead and use the full power Python, and let's simulate this thing. So here I'm going to instantiate the full adder, and then I'm going to elaborate it. So this goes ahead and elaborates. So now I have an in-memory instance of that full adder that I can transform, manipulate, instrument, do whatever I want to. What I'm going to do here is I'm going to apply a pass, and we provide a default pass group, which has kind of a lot of our default passes, but also basically applies our simulation pass, or default simulation pass. So now I have a full adder, which is actually simulatable. So the first thing I might want to do with my full adder is maybe set some ports. So I'll go ahead and use my blocking assignment operator, set A, and then I'll go ahead and set B, and then I'll go ahead and set CN. Then there's, basically this pass group, this default pass group has added some methods. This is the beauty of Python. It's monkey patched some methods into my component, which then you can call to simulate or manipulate the model. So I'm going to go ahead and call sim eval combinational. And so this is going to essentially evaluate all the combinational logic and update the corresponding output signals. And now I can print them out. So there's the sum bit, and there's the cout bit. All right, so now I'm going to apply and try something a little bit different. So I'm going to create a new instance of my full adder. I'm going to go ahead and apply a default pass group. And now I'm going to turn on text wave. All right, so now I've got my text wave. I'm going to call sim reset, which is another method which is added by a simulation pass. And let me go ahead and set the signals again. So I'll, on the first cycle here, I'll go ahead and set 0, 1, and then I'll set it to be 0 again. All right, and then I will call tick, sim tick. Okay, so that sim tick advances time 1 cycle. And then I'll go ahead and set some signals again. So maybe I'll change that to be 1, and I'll change the next one to be 0, and I'll change CN to be 1 again. Okay, I'll tick it again. And then let me go ahead and print out the waveform. All right, so there we go. We were greatly inspired by PyRTL, which also has a super cute little text-based waveform editor, which is fun for demos. You can see here we've reset for 3 cycles. We've set the inputs, and indeed, we're getting the correct full adder behavior. Of course, we also support BCD dumping and much more sophisticated line tracing and such to do kind of more serious debugging. Now, let's say you wanted to actually turn this into hardware. So what we'll do is we'll import a different pass. So here I'm going to import from PyMetal 3 passes backends Verilog, and I'll import that backend. I'll create my full adder again. And then I'm going to set some metadata. So there's a whole metadata system here which you can use to kind of configure different passes. And I'm going to essentially turn on the translation pass. So I'm going to say that I want to translate this full adder. So I'll enable it. There we go. Oops. Verilog translation pass. That's better. All right. And then I'm going to apply my translation pass. All right. And then, assuming everything worked, there we go. So there's the Verilog that got translated. So let's take a look at this Verilog. Nothing against chisel, but you're going to love it. Oh, look how beautiful that is. It's so readable. I mean, partly it's readable because we're writing at a lower level of abstraction. I mean, that's one thing that's going on here. One cute thing we do is in a comment here, we put the Pymetal 3 code, which goes along with the hardware. So you can see that direct one-to-one connection. It's basically what you would expect. So if you're used to kind of certain Verilog patterns and such, there's kind of a nice one-to-one mapping. All right, so that was quick little demo. Phew, it all worked. Great. Good to see that. All right, so let me flip back to my slides here. All right. Okay, so we've used Pymetal 2 and 3 for all kinds of things. So we've done a bunch of tape outs. So for example, here's a small tape out. So this was a tape out in 130 nanometer, had a small RISC processor along with some SRAM, basically about 95% done using Pymetal 2. This allowed us to kind of start to get some experience with kind of strengths and weaknesses with respect to doing chip tape-outs with Pymetal 2. We did another chip out with Pymetal 2. This is more aggressive in TSMC 28 nanometer. So this had a bunch of small little RISC-V cores, which were using some kind of smart sharing mechanisms that allowed them to share the instruction cache and long latency function units. Again, 95% done using Pymetal 2. Pymetal 2 is Pymetal 2 and 3 that is open source, and we think it's a great potentially a great way to bootstrap the open source ecosystem. So if you look at kind of the state of the art in open source HDL simulators, there's Icarus Verilog, Verilator, there's a VHDL simulator. They're working on it. Verilator's working on it. There aren't any kind of real, robust, modern, open source hardware simulators which support modern verification environments. And what I mean by that, there's not an off-the-shelf open source simulator which supports UVM. Now, I don't know if you've done any work with UVM, but you might ask, like, is that really a bad thing? Because UVM is like, you need a PhD in UVM to learn how to use UVM. We would argue that Pymetal 2 might be a better way to do open source design, simulation, and verification because it allows you to use all the power of Python and allows you to use a lot of interesting Python testing frameworks, not just to test software, but also to test your hardware. So we think Pymetal is a great way to bootstrap the open source hardware ecosystem. Okay. And we've actually been using it in a bunch of teaching as well. So we use it in an undergraduate architecture course. We also use it in our graduate ASIC design course. For both of these courses, students choose. They can either use Verilog or they can use Pymetal. And we just use Pymetal's Verilog import features. So all the testing and the function level models and all that is always written in Pymetal. But their actually RTL design work can be in either one. It's perfectly fine. We don't care. So that's nice because the EEs use Verilog and the CS students, they use Python. So it's a good way to get them both taking my courses. We've also used it in a bunch of grants and stuff. For example, we're part of the POSH project, and we've been using Pymetal to build open source on-chip network generators in that context. Done a bunch of publications. This past year has been pretty fruitful. We have an IEEE micro paper, IEEE design test paper, and a DAC paper coming out this year talking about some of our scheduling research in the context of Pymetal 3. Okay, so at the end, in the last part of the talk here, I want to talk a little bit about the Celerity SoC, and then I'd be happy to take questions about either of these different topics. So the Celerity SoC was a very big project across many different universities. It included Cornell, of course, but also UCSD, and Michael Taylor moved to UW, and then the University of Michigan. And it was led by Rajesh Gupta, who was at UCSD. So the idea here is that we were trying to essentially explore new design methodologies in the context of this big DARPA project. And DARPA is like, we don't care what you build, go do something interesting, but use your methodologies. And so it's really fun. So we could build anything we wanted. So what we built, what did we build? So we built a 5x5 millimeter chip in TSMC 16 nanometer with 385 million transistors. I never thought I would be able to work on a chip with that many significant digits. It was such a cool experience. It had 5 Linux-capable rocket cores down here, which we use chisel to generate the Verilog and bring it on into the chip. Had almost 500 tiny little RISC-V cores arrayed in a many-core array. It had a binarized neural network accelerator, which is what we worked on in my group, and it had a bunch of kind of mixed signal, and it was in this really cool open source package that Michael Taylor built for the chip as well. And critically, 9 months from PDK access to chip tape out, which is a pretty remarkable feat for the project. So what was on the chip? So the chip is what we call a tiered accelerator fabric. And what do I mean by that? Well, it had a variety of different heterogeneous components, which together created kind of an integrated system on chip. So at the top, we have our general purpose tier. So this is where we think about running operating systems or doing general purpose computation. It has our massively parallel tier. So this is where we want to scale out and have kind of flexible, energy efficient, highly parallel execution. And then our specialization tier, where we have kind of more fixed function, domain specific or application specific acceleration. And we want to integrate all these together into kind of a unified fabric. So on the general purpose tier, again, the goal here is to essentially do general purpose computation, run legacy operating systems. And so in Celerity, we used 5 rocket cores from UC Berkeley, generated from Chisel. And probably many of you know and love the rocket core. I mean, it's a great kind of baseline, simple, robust core. 5-stage in order scalar processor, supports floating point, can boot Linux. Relatively modest cache sizes. And so we were able to bring that into this chip. On the massively parallel tier, we used on-chip mesh network to tile hundreds of tiny cores into a big grid. So, and the goal here is really to accelerate massively parallel applications in a very energy efficient way. So each of these cores supports the RV32IM ISA, so a much simpler ISA subset. They're also in order and scalar cores. They have much smaller memory, so they have an instruction memory and a data memory, not caches, instruction scratchpad and a data scratchpad. And the network on chip is relatively simple. So wormhole routed, no virtual channels, optimized to be very low latency, high throughput, and very simple. And then there's a specialization tier. And so the here is to get kind of peak energy efficiency on specific application domains, specific workloads. So let me talk more about the specialization domain, because that's what we worked on in my group. So let's take an example. Let's say we want to do something like, map flexible image recognition to our tiered accelerator fabric. So the first step you would do is you'd implement the algorithm using the general purpose tier. Of course, you run it on the rocket cores, you analyze your profile, you try to understand where the bottlenecks are. The second step is you could try to accelerate either on the massively parallel tier or on the specialization tier. And the third step is you might be able to creatively use both of those tiers together to get even kind of an additional benefit. So let's think more about that process with this specific workload. So we were particularly interested in implementing a binarized neural network accelerator. So why were we interested in this? Well, there's 2 reasons. So the first reason was it was a brand new idea in 2016. Well, I know brand new idea, but it was a hot idea kind of just coming out in 2016 with respect to kind of the resurgence of deep learning. My colleague Zhiro Zhang here at Cornell was exploring this idea. It seemed like a cool way to test out how quickly we could build an accelerator. So an accelerator we'd never built before for an algorithm which was still kind of under development. How quickly could we build that accelerator? One reason why the algorithm community was interested is because, for training, we often use kind of floating point. For inference, we can use smaller quantizations, fixed point. Let's push it to the extreme. Let's try to use a single bit for -1, +1 weights. And you can get reasonable efficiency. We can argue whether or not this is a good idea from an algorithmic perspective, but it's certainly a cool idea from an accelerator implementation. How quickly can we build it perspective? Our goal here is to build kind of batch size 1, low latency, high throughput accelerator. So the first thing we did is we characterized it. We characterized it on kind of the general purpose tier running on the rocket cores to try to understand where the bottlenecks are. And first of all, we found that kind of just using the general purpose tier would be 200x slower than our performance target. And so we obviously want to do something to accelerate that. And we can also observe that much of the time is spent in the binary convolution layers. But even if we accelerate that perfectly, it's not enough. So we also need to be able to do the fully connected layers, not just the convolutional layers. So we wanted to build a specialized accelerator, and this is kind of the overall architecture of what we built. So there's a control unit that is in charge of our memory unit, our buffer unit, our compute units. We basically assume that the activations from the last layer are sitting here in the buffer unit. And then we essentially can use this ROC interface, which allows a rocket core to send commands to this accelerator to instruct the accelerator to go ahead and stream the weights into the buffer unit. Then we can use the rocket interface to tell the compute units to do, for example, binary convolution and write the outputs to the output activations. And then we can flip the inputs and the outputs and do the next layer. So nothing too novel here with respect to the accelerator. It's relatively straightforward. The cool part was how we built it. So we built it using high-level synthesis. And the idea here is that we wanted to be able to quickly build the hardware. We only had 9 months and rapidly iterate around both the algorithm and the implementation. So we used Stratus HLS and System C. And we also used Pi-metal. So we used Pi-metal primarily here to wrap and provide kind of adapters and interfaces around the RTL generated from high-level synthesis to allow us to fit it into the rock interface and along with the rocket core. So it was more just to kind of generate and test the high-level synthesis generated RTL. A lot of great benefits of using HLS. So rapid design space exploration, in the kind of the last couple of weeks, we were able to start looking at time enclosure and rapidly iterate. So we were doing a lot of our initial design space exploration with a relatively slow clock period. In the last couple of days, we could push the clock period up and try to see how fast we could go to meet timing of the rest of the chip. We used a latency insensitive design methodology, which allowed us easily to add some pipeline stages kind of at the last minute around the interfaces. But it wasn't all good news. So one of the struggles with HLS is the tools are still evolving. So for example, we literally spent 6 weeks trying to debug a bug in the tool. So it's having a lot of trouble with some data dependent accesses to memory arrays, to multi-dimensional memory arrays, which is literally like you're commenting out system C code and just like praying that this will fix it. So you can figure out which line of your system C code, for some reason, stress HLS is upset about. A lot of these bugs have already been fixed. But HLS is kind of seeing a resurgence, and a lot of the tools are still very much kind of being developed and involved. So we did a bunch of analysis. We were able to show that using the BNN, we're able to get significant improvements in terms of throughput, but also energy efficiency relative to just a single rocket core. In our paper, we talk a little bit about how you can combine the many core with the accelerator. You can store the weights in the many core and not have to get them from off chip. Kind of get this nice synergy between those two different aspects of the chip, and so that was part of the research. But I want to back up a second, kind of circle back to the point of this talk. How were we able to build such a complex SoC? So a 5 by 5 millimeter and TSMC 16 nanometer with 385 million transistors. There's mixed signal design in there. We're doing all the front end and the back end. There's no like front end handoff, like we had to do it all ourselves and the whole team. And we did it in 9 months with 10 core grad students with very little tape out experience across 4 locations. How is this possible? I can say with confidence that this was only possible by leveraging open source software and hardware. It's absolutely critical to the success of this project. So just to drill down on that for a quick minute, the RISC-V was critical to the success here, okay? So leveraging the RISC-V open source ecosystem. So we had an open source tool chain right off the bat with the compiler for both the many core and the rocket cores. Using the ISA allowed us to quickly extend it, for example, adding the rock interface and yet leveraging that to compose it with HLS generated accelerator. Being able to use the rocket core off the shelf and also some previously developed IP for the many core. And then also just being able to leverage lore and guidance in the ecosystem about what works and what doesn't with RISC-V tape outs. So it's super big help. In addition, the base jump infrastructure being developed by Michael Taylor was super helpful from a lot of the more practical system level aspects. So base jump includes kind of an open source socket, an open source package, and an open source board design, which allowed us to plug in the chip when we got it back and be able to test it right away. So that was super useful as well. And all that's open source. And then, of course, we try to contribute back. So if you go look at openstellarity.org, there's a lot of the IP on there from that went on the actual chip. And even, for example, we use Gem 5 for some of the testing and such, and we contributed RISC-V Gem 5 packages back on the simulator front. So we had a bunch of publications in IEEE Micro and VLSI about various different aspects of this chip. Okay, so I'd like to conclude with a call to action. So the goal for open source hardware is to get your starting point not at the bottom of the mountain, but all the way up here. So climbing, it's more like climbing a hill, not like climbing Everest, to be able to do hardware innovation, to try out your new hardware chip startup, right? So that's the goal of open source hardware. In order to make open source hardware a success, okay, we need developers, and we need developers who are idealistic, who have lots of free time, and are going to work for free. So does anybody know a bunch of developers who are super idealistic, have lots of free time, and will work for free? Well, hopefully some of them are sitting here, in the audience. I mean, that could be students, and you better believe students help bootstrap the open source software ecosystem. And now's the time for students to get involved in the open source hardware ecosystem, essentially by contributing not just to the IP side of things, but also to a lot of the excitement going on in the EDA and the tool side of things. And there's a lot of great work going on at UCSC exactly in this area. And I would argue that as academics, we actually have a very practical and we might even say ethical motivation for using, developing, and promoting open source electronic design automation tools and open source hardware designs. I mean, what are we in? We're in the business of like knowledge generation. And what better way for knowledge generation to contribute to the open source hardware ecosystem as architects? So hopefully all of you will take that to heart. I know some of you are already doing this, and I congratulate you and want all of you to continue these contributions. All right, so here's my research group. I'll end with this slide. I'm happy to take any questions about either our work on PyMetal 3 or on our work on Celerity, or just on the open source hardware ecosystem in general. I'm glad I had a chance to come and share all this with you.
Great talk, Chris. Happy to take any questions from the audience. I can read from the chat or Q&A section, or you can even raise your hand. I can turn the microphone on for you. While they're preparing their questions, maybe, and a couple I had from during the talk. So one of the things I've always loved about PyMetal is this multi-level representation, where you can kind of very easily go back and forth between cycle level, function level, etc. Do you have any techniques or tools to make it easier to, I don't know, maybe verify or just somehow validate that these different representations are equivalent for some notion of equivalence or something?
Yeah, that's a great question. So we don't have any formal techniques. That's a super cool research idea. But what we do have is a way to build your testing infrastructure to allow it to be able to leverage across different modeling levels. So, and this is more of design patterns than specifically built in the framework itself. But by using kind of a stylized way of building your components, you can write tests for your functional level model and then reuse all those tests for your cycle level and your RTL model. And that's often what we do. So what you'll do is you'll write, for example, a bunch of functional level tests for your accelerator. Then you reuse all those, maybe the cycle level modeling implementation. Maybe you augment them with some new tests, which are more kind of explicitly trying to test the cycle level behavior. And then you might augment that. You reuse all those on the RTL model, and then maybe augment them some there. One thing what we've done is built into PyMetal 3 the ability to automatically insert interface adapters. So this allows you, when you compose, for example, cycle level and RTL models, where the interface are consistent but have a mismatch with respect to abstraction, we provide hooks to allow you to register an appropriate adapter to insert at that point. These are sometimes called like transactors in System C to allow you to cross that modeling interface. And so that can be really useful too for that kind of mixed level testing. Formal methods is a super interesting area that I think we haven't explored much yet.
So I have a question while they're typing some questions on the chat. So one of the main benefits of PyMetal is the Python infrastructure that you have around. If you are using the PyRTL, they have the similar thing. So from your point of view, what's the main difference that you see as the main difference between these two approaches?
No, I love PyRTL. PyRTL is great. I mean, the more the better in terms of ecosystems and frameworks.
But I'm talking about technical difference. What is the technical difference you see between them?
Sure. I mean, PyRTL as originally formulated, although all projects are under development, was at a lower level of abstraction. So doing kind of higher level behavioral modeling was not kind of in the domain of PyRTL. So the idea of like everything needs to be synthesizable, that was one of the strengths too, because it allowed you to kind of, be more precise in terms of everything has to be synthesizable, everything is hardware, and also provide abilities to kind of transform or synthesize some of that. So I think that was one key difference. Whereas PyMetal 3 takes much more kind of a holistic view of building kind of multi-level models that span the stack. But I think both frameworks have a lot of strengths and weaknesses. So I'm not willing to argue that PyMetal 3 is like superior to all other frameworks. I think it has its place and its pluses and minuses, and part of the research is figuring out the best of each and trying to blend them all together. But I think the multi-level modeling would be a great example where there's a concrete difference. Okay.
We have one question that came in from a student. Reading some quotes. Do we have any test matrix like UVM has coverage include verification is done 100%, I guess. So yeah, so in other words, what kind of verification coverage tracking do you have?
Well, I think any UVM verification engineer which is willing to claim with strong credibility that their verification is done 100% should be fired. I mean, like, I think, verification is never done, but I absolutely 100% see what you're getting at. One of the beauties of using something like Python is we can leverage a lot of the Python coverage tools, right? And so you can leverage standard Python coverage tools if you want to do coverage analysis. Now that's like line coverage, not functional coverage. We could certainly add kind of functional coverage, and we have looked into that. But one thing we're a little bit more excited about, to be honest, is trying to co-opt software testing methodologies to make it easier to do hardware testing. Because if you go look at all the open source projects, very few of them have like robust industry grade UVM test benches. And, one reason why is like people, it's not just that there aren't open source simulators, they're a huge pain to write and they're very complicated, and open source hardware engineers aren't getting paid to do this. They want to do the fun part. So let's make it so easy to do testing that you almost don't mind. And if you look at open source software, that's the way. Like, people are proud of essentially like having that Travis CI badge on there and having their test suite and continuous integration. And so, for example, one thing we've done, and we were doing some research on this, is leveraging something called property-based testing. So property-based testing, like QuickCheck in Haskell. So property-based testing is kind of this really cool way to do testing where you have a systematic way to generate test inputs. And then on a failing test case, there's automated ways to do test case reduction. It's like magic. It's super cool when it works, because you get this random test case with like 100 transactions and it shrinks it down to like 2 transactions. And you're like, oh, I know what's wrong. Whereas you're waiting through 100 transactions to try to debug something is super painful. We didn't have to build that from scratch. All we had to do was leverage current open source infrastructure and adapt it for hardware testing. I'm far more excited about that, because that kind of stuff is super productive, super flexible, and anyone can do it. So can you do things like functional coverage and UVM and kind of more kind of classic approaches? Yes. But we don't do that. We try to make testing super easy and super fun and super lightweight. And that's kind of more of our approach. That's a great question, though.
Kind of dovetailing on that, I believe in one of your slides, in the middle of your talk, when you're mentioning the verification capabilities, was I correct in hearing you say that you used the term PyMetal 2 a few times there? So is that suggesting that some of this verification stuff is, in progress to being ported to PyMetal 3 or something, or?
No, I think we were using PyMetal 2 to do some of the testing for Celerity, because that was before PyMetal 3 existed.
Okay.
I would actually argue PyMetal 3 is kind of a little bit more robust in the testing side of things, because that's where we've started to explore this idea of using hypothesis. So PyMetal 3 is ready to go. I mean, the one thing PyMetal 3 needs is better documentation, and it's on our to-do list for this summer. So we're definitely gonna working on some of the documentation this summer for PyMetal 3. But we've used it in an unnamed GF 14 nanometer tape out, and an upcoming unnamed another GF 14 nanometer tape out. So it's been used in big tape outs, but it's also been used in teaching. So I used it in my ASIC course last year. It wasn't quite ready. This year I used it much better. No better way to get a framework and test it than to get 20, 40 students banging on it and yelling at you when they're like, this error message is horrible. So that was quite successful. And we've also started to use it in some of our research as well. I mean, being perfectly honest, a lot of what we've been using it for lately is more in the RTL modeling, partly because we've gotten a lot better at Gen 5 modeling than we were like 5 years ago. So the RTL modeling is primarily what we've been doing lately.
Great. Maybe pause for more student questions or other co-panelists, I guess.
Well, can I ask a question of a panelist since we're on a
Yeah.
panel?
Go ahead.
I would love to hear from maybe Matt about how, I've been impressed with kind of the momentum around Open RAM and contributions. And I'd love to know kind of like any tips or tricks to how you've been able to build momentum. I think with PyMetal 2, we were kind of a little bit cautious. We didn't quite know if it was a good idea yet. We addressed a lot of our concerns. PyMetal 3 we're much more excited about. We're much more excited to be advocates for it. So I'd love to hear your experiences in terms of how you've been so successful with Open RAM.
I think the only reason is we're the only people in the field doing that.
That's it. You have a monopoly.
Yeah, it's a monopoly. And really, I think that's it. I mean, we've actually partnered with recently with Yale, Rajit. They had their asynchronous memory compiler,
Yep.
and we're going to try to kind of bring some of those features into it because they forked off of OpenRAM a couple years ago. The one thing I think that we have not been successful on is actually engaging with other developers, and we're trying to do that more now because we can't push it on our own. You
And
mentioned the infinite like workforce of people. We need
Yeah.
to harness that.
I think one thing that's interesting, and maybe I should mention this, is being an open source developer, it's like a kind of a different way of thinking about things, and it's a different way of engaging with the community. And an open source software, and basically people that do system software research and kind of are really familiar with that process. Some of this is kind of teaching hardware designers, engineers how to kind of like be very productive in the open source ecosystem with respect to like monitoring pull requests and engaging people in the right forums and having regular releases and having kind of the right way to document change logs and kind of robust test suites and continuous integration. And so part of what we've been learning about that too. So I can't tell you how important packaging is. Like that's made a huge difference.
Yeah.
So even something like that. So anyways, it's great to see some of the success here at UCSC with respect to open source hardware. It's great.
I might push back on one of your points on your open source development list of saying you need to do it for free. I mean, we can get grants. We have gotten grants. We're paying students with grants to do this, right? So
absolutely. And I think those grants, and I mean, Matt knows this, those grants aren't easy to get, but they're super worthwhile. And I hope that we're able to continue to get those. We were fortunate to get some NSF funding for Pymetal 3, and that definitely helped. Absolutely.
Yeah. Actually, Chris, can I talk to you for a minute after we're done?
Sure.
For like 1 minute.
Yeah, of course.
Any more questions from the audience? All right, well, maybe we'll go ahead and thank the speaker one more time for a great talk and sign off.